In this problem, we have a 4-meter long steel rod must not stretch more than 3 millimeter. 3 millimeter, this is the deformation. And the normal stress must not exceed 150 megapascal, or 150 times 10 to the power 6 Pascal, when the rod is subjected to a 10 kilonewton axial load. Knowing that E, modulus of elasticity, equal to 200 gigapascal, or 200 times 10 to the power 9 Pascal, determine the required diameter of the rod. So in here we have the length of the rod equal to 4 meter. The maximum deformation equal to 3 millimeter, or 0.003 meter. And the normal stress must not exceed 150 times 10 to the power 6 Newton over meter squared, when the rod is subjected to a 10 kilonewton axial load, B equal to 10,000 Newton. Knowing that modulus of elasticity E equal to 200 times 10 to the power 9 Newton over meter squared. Determine the required diameter of the rod. So here we are asked to find the diameter of the rod. So to find the diameter, we need to find the area, because area is equal to pi over 4 d squared. And the goal in here is to find the diameter, so we can solve for the diameter. So diameter will be equal to the square root 4 times area divided by pi. And this is the equation that we will use to find the diameter. And to find the diameter, we need to find the stress. In this problem, we can find the area in two different ways. We can use the stress equation or the deformation equation. And both equations we can use because we have the values that we need to find them. So the stress is what? So we know that stress is force or applied load divided by area. And the deformation, which is derived from Hooke's law, is equal to applied load times length over area times E. So in these two equations, we can solve for A, and then the question will be, which one do we use, the stress or deformation? In these types of problem, you solve for you use the stress equation and the deformation equation. If you are given all the needed information, use both of them and choose, in this case, the larger value and apply it in the diameter equation to get your required diameter. So for the first equation, for the stress equation, we can solve for area equal to applied load over normal stress divided equal to the applied load. We are told it's 10,000 Newton, The normal stress is given to 150 times 10 to the power 6 Newton over meter squared. So the area in here will equal to 66.667 times 10 to the power minus 6 meters squared. Or we can say that area is equal to 66.667 millimeter squared. So this is the area that we got using the stress equation. Now let's use the area from the deformation equation and solve for area. So area will equal to PL over deformation times E. So area will equal to, so the applied load is 10,000 Newton. The length is 4 meter divided by the deformation is 0.003 meter times modulus of elasticity 200 times 10 to the power 9 Pascal. Area will equal to 66.667 times 10 to the power minus 6 meters squared, or we can say 66.667 millimeter squared. So in here we have these two area. So which areas we're gonna use? They are the same. So, and again, if they were different, then we should the larger area will govern. So we will take this area and plug it into our diameter equation. Diameter is equal to the square root 4 times the area, which is 66.667 diameter equal to the square root 4 times 66.667 times 10 to the power minus 6 meters squared divided by pi. So the diameter will equal to 9.21 millimeter. So that will be your diameter. This is the required diameter. In this problem we have a nylon thread is subjected to a 10 Newton tension. So this is our load. Knowing that modulus of elasticity E equal 3.2 gigapascal, that the maximum allowable normal stress is 40 megapascal, and that the length of the thread must not increase by more than 1%. So that's your deformation. Determine the required diameter. So here we want to find the required diameter of the thread. So here we're dealing with a nylon. That nylon is subjected to a load equal to 10 Newton. Knowing that the E is 3.2 times 10 to the power 9 Pascal. The maximum allowable normal stress max, 40 times 10 to the power 6 Pascal. And the length of the thread must not increase by 1%. So your deformation should not increase more than 1%. Determine the required diameter of the thread. So here we want to find the diameter. Since we are dealing with the diameter, that means that the cross-sectional area of the nylon thread is circular cross-section. Area equal to pi over 4d squared. So the goal in here is to find our diameter. So let's solve for the diameter. Diameter equal to the square root 4 times area divided by pi, and that will be the equation that you will use. And here we need to find the area in order to find the diameter. Based on what we have in here, you know, we first thing, I like to write down the equations that we can use. So we can use the stress equation, which is load over area. Can we use this equation? So we have B, and we need to find the area. So, and we have the maximum normal stress. So this equation we can use. Another equation is the deformation equation, PL over AE. We we can find the L, the ratio between the between this and this, between the deformation and the length, we can get it from the 1%. That's fine. We have the load and we have the E, so we can also use this equation. So we can use both equation, and the diameter that we can use is the larger diameter. So let's use the first equation, which is the stress equation. And in both cases here we want to find the area. It will be load over stress equal to, the given load is 10 Newton divided by the maximum allowable stress, so area in here will be 250 times 10 to the power minus 9 meter squared. So now we can plug in this found area into our diameter equation. Four times 250 times 10 to the power minus 9 meters squared divided by pi. So the diameter in here will equal to 564.19 times 10 to the power minus 6 meter, or we can say in millimeter 0.564 millimeter. Next, we can use the second equation, which is the elongation equation, and we can solve for A, and that will give us BL over the deformation times E. Now remember, in here we have L over deformation, which is the reciprocal of the strain, because strain is the deformation over L. Now what we said it's 1%. We can assume that our length is 100, and the and here 1% of 100 is 1, so 1 divided by 100 is 0.01. So that is your strain. So here we can rewrite this equation in this way: P times E over the stress over the deformation over L. So the given load is 10. Sorry, this divide by the strain, which is 3.2 times 10 to the power 9, divided by this this value right here, which is the strain, which will be 0.01. So area in here will be equal to 313 times 10 to the power minus 9 meters squared. So now we can plug in this found area into our diameter equation. So D will equal to the square root 4 times 313 times 10 to the power minus 9 meters squared divided by pi. So the diameter here, we will have it 630.78 times 10 to the power minus 6 meter. Or we can say that diameter is 0.631 millimeter. So which diameter will we use? We will use the larger diameter. So this is the one that we will use, this diameter. Hi, in this problem we have a 4 millimeter diameter cable. So this is 4 millimeter diameter cable BC. B and C is made of steel with modulus of elasticity 200 gigapascal, knowing that the maximum stress in the cable must not exceed 190 megapascal, and the elongation of the cable must not exceed 6 millimeter. Find the maximum load B that can be applied as shown. So let's write what we have. We have a 4 millimeter diameter, D diameter equal to 0.004 meter. That's the diameter for cable BC, made of steel knowing that the maximum stress or maximum normal stress and the elongation of the cable must not exceed, so the elongation find the maximum load B. So So we want to find the maximum load B in here. So it's a good idea to draw the free body diagram in here. So at A we have a pin support right here, and pin support will have a reaction force in the Y direction and a reaction force in the X direction. And at pin B we will assume that we will have a tension at the cable, and we call this force BC. And to know the angle in here, we can use the triangle relationship. So 3.5 plus 2.5 is 6, and right here is 4. So so this is a right triangle. We can use the Pythagoras theorem. 6 squared plus 4 squared will give you the square root of 52. So we can use this relationship in here, and we can break the force in the cable BC, which we are interested in, into two components, the vertical component and the horizontal component. And this angle can be the same as this angle in here. Our goal now is to find a relationship between the load B and the force of the cable FBC. So let's use the equilibrium equations, and let's say that the sum of the forces going up in the y direction equal to 0. So here, so it will be A, the reaction force at pin A, and the second reaction in here, which will be FBC times, so this is adjacent, so it will be 6 over 6 over square root 52. So, and it will be in the negative direction, so it will be force at BC times 6 over the square root 52 equal to 0. Next, the sum of the forces in the x direction equal to 0. So we will have AX negative, and the next one is minus B, and positive FBC, which is this one, FBC times, this is opposite, so it will be 4 over square root 52. So this will be 4 over square root 52. But as you can see in here, can we relate the sum of the forces in the x direction equation between the force in the cable and B? No, this one we can't use. The y equation we cannot use. The sum counterclockwise is positive. The sum of the moments at A equal to 0. So here we will have like a circle, like a wheel in here. So the load B, when we apply a load like this, it will move the circle counterclockwise. So it will be positive. So it will be P times, and it is a distance of 3.5 meter. 3.5. The next load is this one, FBC, right here, which will be 3.5 or it will be applied right here at a distance of 6 meter, and it will move the circle in this direction clockwise, so it will be negative FBC times 4 over square root 52 times the distance of 6 meter equal to 0. So I think we can use this to find a relationship between the between B and the force in the cable BC equal to FBC 4 over square root 52 times 6 divided by 3.5. So here P will equal to 0.9509 FBC. So here we were able to find an equation that relates the applied load B and the force in the BC cable. So now we can use the stress equation to find the force. So we know that stress is equal to the force in the BC cable divided by area. So our goal in here is to find the force in the BC cable and plug it into this equation right here. And also we can use the deformation equation, where we can solve for force in the cable BC times L over area times E. So here we can also solve for this and plug it into our equation in here. So let's start with our stress equation, and let's solve for FBC. So FBC, so this is stress, will equal to the normal stress times area. Now from the problem we are given that 190 times 10 to the power 6 Pascal times the area, which will be pi over 4, times the diameter we said is 0.004 meter squared. So in here the force in the BC cable will equal to 2.388 times 10 to the power 3 Newton. We can also use the deformation equation, and we can solve for FBC equal to the deformation area times E divided by L. So the deformation, we are told it cannot exceed 0.006. Times the area, which is pi over 4 times 0.004 meters squared, times the modulus of elasticity is 200 gigapascal, all divided by the length, and the length in here will be our square root 52, the triangle that we found its hypotenuse, the square root 52. So this will be 2.091 times 10 to the power 3 Newton. Alright, so here we have two force values, one from the deformation equation, and we have another force value on the cable from the stress equation. Which one should we use? The larger value or the smaller value? So here we will use this force, the smaller value, and we will take FBC that we found and plug it into our relationship that we found from the free body diagram. So that will give us B equal to 0.9509 times the force, which FBC, which is this one that we have, 2.091 times 10 to the power 3, so that the load is 1.988 times 10 to the power 3 Newton, or we can say the load is 1.988 kilonewton. So this is the load that we need to apply at this location right here to satisfy the maximum normal stress that we have, with a given the cable diameter and cable and that the cable is made out of steel, and the maximum stress to be 0.006.